The next thing we have is the subcooler. So why are we going through this mechanical subcooling business? We're creating all these complicated things that affect everything and cause it all to go to crap. Why are we doing that?
Efficiency of your valves.
All right.
Engineers designed it to work that way, let it work that way.
Increase horsepower.
There's a couple things that, as technicians, it benefits us. So it's great for us. But I can promise you, the folks writing the checks don't care. Right?
You don't say.
They're writing the checks because this little subcooler cranks out dollar bills. That's why. Right? So how much and what? I've explained this a few times in a couple different ways. Since I've got you in the classroom and we can look at some stuff, here's a legend that breaks this out and makes it really obvious, right? If we look at this legend, we can see I got a Rack A and a Rack B subcooler listed on the legend, right? That's unusual, okay? But what this means is I've got a satellite subcooler on this rack, and it's subcooling A and B rack. That's what it's doing. Well, since we're doing that on this store, they all work this way, but it's going to put it all in the same legend, which makes it really easy to see. Okay? Found this the other day by accident. By the way, I was looking for something else. So I was like, perfect for class. Very happy that I stumbled on that. All right. So one thing to note about my rack subcooler. Let's look at A's. All right. This is MBTUs. Okay. So a little over 60,000, right? 5.5 tonnage.
Mm-hmm.
You guys got that?
Not quite.
No, it's 5.5 is right. 5 3/4.
Yeah.
5 3/4. Okay. All right. Yeah, just ballpark it. Around 5.5 tons. Okay. So my subcooler is about 5.5 tons, and it's doing that at a 47-degree evaporator. Okay. You guys got that?
Yep.
Remember I said subcooling is similar to air conditioning pressures? Yeah, that's kind of making sense. Right, this one's a little higher, but that's the idea. Okay? So I've got that going on. All right. Well, here on this rack, I just happen to have on compressor number 4, I got a subcooler. I got a compressor that's about the same capacity refrigeration-wise, about 5.5 tons. Okay. So I got 5.5, 5.5. Call those pretty dang close to the same. This one is my suction on the rack, minus 27. It's a cold rack. Right, got bunkers and ice cream on this. Right, it's a minus 27-degree rack. It is doing that with 15 horsepower. Right, this is what we were talking about by running a lower suction pressure causes an exponential increase in power consumption or loss of efficiency, however you want to look at it. Right. Well, here's an example. I got a 15 horsepower compressor that's only giving me 5.5 tons. Right? Right? But it's doing it at minus 27.
Damn.
Okay? Does that make sense?
That's great.
We're all good. We're all good here. If we need to stop and go through this, if this is news to you, we can stop and go through that a little more.
That's a big boy.
What's that?
Yeah.
So this is the big boy, right? On this rack, on this particular rack, I got 3 small body compressors, and I got the big boy. Yeah, this is the big boy. Yeah, right. Okay, so all that's fine and good. Great. Oh, what do we got here? Okay, so on this side I've got these are my satellite compressors for my subcooler. That's what I'm saying. All having it on one page makes this really easy. Okay, if I look at compressor 1 and compressor 2, these are their MBTUs. I add those together. They're not exactly the same, but they are really close to the same load as that.
61.
Yep.
58.
Yep, 62. So 62, pretty close to 64. 2 horse or
4.5.
Holy
You
Christ!
get the same compressor for a third of the horse.
There it is. There it is. All right. So if I turn off my subcooler, I need another one of these at 15 horse. Or I can turn on my subcooler and do it with 4.5. 4.5 horse. That's significant, right? That's not a small amount. And here's the other thing that's wild about this one.
Auburndale savings.
I'm subcooling to 60 degrees. this is one of my warmest racks.
Yeah.
That's really high. Most of our racks are running lower than that. So this becomes even more pronounced as we go down to subcooled temperature, right? Why is that? Every BTU that I'm removing from that liquid is a BTU that my compressor has to do. They're 1-to-1, right? So if I remove that energy from my liquid, then my compressor doesn't have to work as hard. That's it, right? So if I can do that at 47 PSI instead of minus 27, it's a giant energy saver. Took 15 or 10 horse, right? About 10 horse, ballpark, just on this one subcooler, at 60 degrees.
Well,
That's pretty wild.
That's only half of your satellite rack too.
Right, yeah, and it's running the other half too, right, the other rack. Yeah, so anyway, that's the why for our customers. That's why our customers paying for it. Okay, because like I said, it's printing out dollar bills. How's it doing that? It's printing out a rebate on a power bill every month. That's how it's doing it. Okay, so that's why they want it, right? Now, the impacts of this, making this refrigerant more efficient, okay, because that's what we're doing. We're making the same refrigerant more efficient when we cool it, when we subcool it, all right? When we pull those extra BTUs out, that same refrigerant can now do more work. Therefore, I need to flow less of it. That means my copper pipe leading to my liquid line, leading to my case, my TXV, is going to be smaller. My TXV itself is going to be smaller. All right, that's what that's going to give us. Well, what it's going to give us as technicians, this is the big one for us, is I don't have this wild temperature swing of my liquid from summer to winter. Right? I'm not feeding it with 100-degree liquid in July and then feeding it with 50-degree liquid in January. That would, because I just told you that changes the size of my valve. And we'll see that when we go into sizing TXVs later. All right? When we do that, that means technically, without the subcooler, we need to be adjusting our TXVs for summer and winter. Right? There's two reasons. One is the liquid temperature. The other is the pressure differential, and we'll get into that when we get into TXVs. But those two things, without that mechanical subcooler, there are customers up north, God love them, that have to set every TXV in their store 2 times a year. Because they don't have a subcooler and they have nothing controlling that liquid pressure. Right? That's old school, that's how they've always done it, so they're still building that way today. You know, and it's just high maintenance. Just high maintenance. So one of the major implications of this, as a service technician, I never set a TXV on a store with a subcooler when the subcooler's off. Right? Now my liquid is going to be more efficient. That means my TXV is going to be bigger when it's subcooled liquid, smaller when it's not. Well, if I adjust it when it's not, it's going to flood when I turn that subcooler back on. Right? This happens. We find this. We find this as technicians. We find a problem with the subcooler and we fix it. Right? We fix 98% of all the cases in the store all of a sudden start working that weren't. But the two that our tech, the previous tech, the whoever, somebody else, has adjusted because they were actually going into alarm. Right? When we turn that subcooler on, those two guys are now flooding. Right? We see that. We see that happen. Okay? So as a best practice, as a technician, never adjust the TXV with the subcooler off. Right? We start with the subcooler. We don't start with the case.
They should put like a huge sign in the rack house.
Right.
saying that.
Warning, danger.
I have found that pretty much every single store I go to.
Happens all the time.
Subcooler install on this.
And they're always changed too. That's the fun part about like the cases that are flooding back.
New
They're
valve.
They're always new, and it's all, this case just.
Put that in
problem.
scope of
It's a
work.
problem.
The TXV's a problem, change.
For us, it's fine.
Yeah. Yeah, so anyway, that's a lack of education is what causes that, and that's why we're talking about it today.
Yep.
Okay? All right, so how's a subcooler work? All right, well, there's a few different versions of this, but they're all very similar. They're plate heat exchangers is what they are. You've heard that term. This one is a brazed plate heat exchanger. You'll hear that term too. All right. There is nothing unique about the heat exchangers we're using on a subcooler. They're the same heat exchangers that are used in the HVAC industry, widespread, right? We use this for chilled water. We use this for CO2, we use this for steam, we use this for, any time we're trying to transfer temperature of two different media, we can use a plate heat exchanger, okay? Super common. Nothing unique about this one at all right? What this is, if we look at my blue side, all right? The blue side is the side that's going to do the work. We call this the primary side, all right? The blue side's the side doing the work. It's my primary side. It is an evaporator, right? It is an evaporator. That means it's gonna have a TXV, right? We're going to send liquid refrigerant into it. We're going to boil that refrigerant, change state. That latent heat exchange is going to absorb heat, and it's gonna come out as a subcooled vapor. Make sense? Just like any evaporator. What temperature is that gonna happen?
I was gonna not say.
Superheat, excuse me, superheat vapor. Right.
Say, you got problems.
What temperature is that gonna happen? What temperature is that gonna boil at?
That's actually
What's that?
saturation.
Right? How do we control that?
EPR.
Okay, so we're gonna,
Yeah, we're good.
on the primary side, we're gonna see an expansion device, right? On the inlet, on the outlet, we're gonna see an evaporator pressure regulator, because it's an evaporator. Make sense? Right. On the secondary side, doesn't get any simpler than this. We're gonna flow in what we want to chill, and it's gonna come out chilled. Right? It is the heat that we're absorbing with the primary side. All right, let's think of this as a refrigerated case,
Yep.
right? The primary side is my evaporator, the secondary side is my air, is my fan. Right? If I unplug my fan, what's gonna happen to my evaporator?
Ice up.
No, ice up. What's going on with the refrigerant inside?
It's not boiling off.
It's not blowing off, I'm flooding. Right? That's gonna happen here. If I turn off my fan, what does that mean? That means I have no heat on my liquid leg.
Well, I mean, if you're shutting off, yeah.
Right. So going back to our surge and our ambient setup.
Well, I mean, if you're shutting off the subcooler, if you're shutting off that side of the subcooler, you're shutting the rack down.
All right.
No.
So
necessarily.
here's how we're gonna set this up. He's got valve one. If I turn off my subcooler, am I not shutting the rack down? Well, I'd pump down the rack if I close the liquid line, right? But that's not what we're gonna do. When we shut off a subcooler, we're gonna leave the secondary side open. Our refrigerant's gonna flow right through the subcooler. I'm just not gonna refrigerate it. I'm gonna turn off the liquid line solenoid feeding my expansion valve. So I've got no refrigeration effect. All right, that's the side I'm closing, the primary side. My secondary side is just gonna flow right through. All right, so what I was just talking about with my heat going away and I can flood, all right? That's gonna happen when my drop leg gets cool, because that is my heat. When I'm bringing my drop leg into my heat exchanger, the heat that it's bringing is what we're absorbing with refrigeration. Well, if there's not enough heat, we're not gonna absorb it. We've got liquid coming out, we're flooding, right? So going back to your drop leg sensor that's dangling or bad, is that important? Yeah, it's gonna cause my subcooler to bypass, right? To close that solenoid on the refrigeration side, so we don't flood, okay? So we don't flood. When's that gonna happen? When that drop leg temperature hits the temperature of my subcooler's requirement, right? That's also, if I've got it, it's gonna open my ambient surge, right? So if I walk into a rack and I see my ambient surge energized, my subcooler better be off. The liquid feeding the primary side. Does that make sense?
Dang,
All right.
I suck at my job.
The other little bit, and I could probably do 4 hours on this heat exchanger, I really find it fascinating. I know you don't. So let's speed through this. The other piece I do want you to notice is that it's counterflow. All right? So that means my primary side is flowing that way and the secondary side is flowing that way. Why do we do that? The reason is the coldest spot on this entire thing is right after my TXV. Well, that's right here, okay? The warmest refrigerant I've got on this whole thing is this secondary refrigerant coming in. before any work is done to it. Well, that means on the primary side, this is the warmest part of my evaporator. So I bring in the two warmest together, right? And then I have the coldest, where it comes out is the coldest spot on the primary side. So it's the coldest that it's gonna be, right? So technically it's counterflow, but really what I'm doing is making the warmest and the warmest match and the coldest match, right? Why am I going through that? The challenge we have as technicians is I got 4 pipes that look the same, right? Many stores, there are 4 insulated pipes that look the same. Sometimes one of them's not insulated, sometimes they are, right? When I walk up to this subcooler, I gotta figure out what's my primary side, what's the inlet and the outlet, what's my secondary side, what's the inlet and the outlet. I gotta figure that out, right? So that's why I'm going through the construction of this, because once you understand this, it'll be very easy to figure out. You'll never stumble on that again. You'll walk right up to it, you go, oh, that's obvious, right? So the way that I recommend, and you can do it any way you want, right? My recommendation is look for the TXV. Look for your expansion device, right? That's gonna, if you find the expansion device, you know you are right here. From there, you can figure it out. You can figure everything else out. So on this picture, here's my TXV, right? I can see it. Okay, there's actually 2. There's one hiding right behind here, on this particular one. But that means that's this corner. That means my liquid coming in is right here. That means my liquid coming out is right behind it. Right? I also know that that's my primary side, because there's my EPR. Right? Blow that up a little bit so you can see a little better. There's my TXV. Okay, like I said, there is 2. There's one hiding right there. All right, if I can find that expansion device, and that'll be the most obvious thing, I know that's the coldest spot, right? I know immediately next to it is gonna be my liquid coming out. I know immediately above it is gonna be my suction. It's gonna have my evaporator on it, which leaves the oddball corner, gonna be my liquid coming in. This is a drawing of the picture that I just put up. This is that setup, okay? This is an older school idea, but there's a bunch of stores that are set up this way. All right, here's my liquid coming in, and they're not showing it, but this liquid coming into these valves is this liquid. There's gonna be a T. It's just literally gonna tee off and come down here, and it's gonna feed 2 solenoids. It's gonna feed 2 TXVs. They're gonna be different sizes. Right? One's small, one's big. They're gonna be labeled that way, large and small, or big and small, however. All right? And they're not gonna be dramatically different, but you know, you'll see a 3 and a 5, you'll see a 5 and a 10 on some of the big boys, okay? All right? That TXV is gonna feed my evaporator, which is my primary side of my subcooler, and I'm gonna come out the suction, and here's my EPR, and then I'm going to the suction, okay? For that circuit. My refrigerant is coming in here, and it's coming out chilled. It's just that simple. Now, the way this is gonna stage, right? If I'm gonna have a cut in and a cut out for this solenoid. Right? Let's say my target is 50 degrees subcooling. I want 50 degrees subcooling. I'm gonna set this valve, this solenoid, to open when the liquid leaving temperature, this blue pipe, right, hits 50 degrees. Okay? It warming up. Right? When it warms up to 50 degrees, I'm gonna turn this on. Then I'm gonna set up a stage. If this hits 55 degrees, I'm gonna switch, I'm gonna turn this off, and I'm gonna turn this guy on. At 60 degrees, if this thing is still climbing in temp, I'm gonna turn them both on. Right, I'll have 3 stages of subcooling. Right, so when I walk into this store, I may walk in at maybe 55 or 60 degrees. That's okay. It's in its range. Right? That's the downside of using this setup, is I gotta have a big enough gap for those to cycle. Okay? Right? Maybe even be 20 degrees. You know, we've seen that. I'll walk in, it'll be 40, and then 50, and then 60. That means my target's gonna be 50, and I may be running 10 under or 10 over. Right? It's okay. That's just how it works. Right? So just be aware of that. Now, How do I set these valves? What's different about this than just regular setting TXVs? There is a phenomenon that occurs on this subcooler that we just don't see very often on a regular evaporator. It can still happen, but it's just not very common. And that is, if I think of the subcooler as a bucket, right? I'm gonna fill it up with liquid, but not all of it. If I fill all of it with liquid, I don't have any room for that refrigerator to boil. I gotta have some space for it to boil, okay? If I have no liquid in there, I'm not gonna boil at all. It's not gonna refrigerate. If I put that liquid somewhere in the middle, right, it'll boil really well, but I just won't have enough of it. So I wanna get, that, and this is the same for any evaporator, this isn't anything special, right? I wanna get that percentage just right, so I boil all of it until the last little bit, because I have to have some superheat to protect my compressors, right? That's what I want. Well, if I run this guy that close, when I go to set my superheat, it's really easy because this is so efficient, I don't have the air, it's just plate, right? It's really easy to overfeed and flood, right? When that happens, my bulb that's sensing that is not real far from that heat exchanger. And it's gonna happen so fast and so much refrigerant's gonna flow through there, it's possible that this is all gonna be liquid until somewhere out here. That happens, right? We don't see that very often on a case, but we will see that regularly on a subcooler. So what does that mean? Well, that means I've got liquid refrigerant in here instead of vapor, and it's not superheated,
Rip.
right? So what does my TXV think's going on? Starving. Thinks it's starving. What's it gonna
More
do?
liquid, more.
More liquid.
It's gonna open. Ding, ding, ding.
Why does it think it's starving?
Because I don't have superheat. It's not cold. It's not a cold suction line. It's a warm suction line, and the warm is telling the TXV,
Oh.
refrigerate more.
Yeah, your superheat's gonna be higher even though you're flooding.
Yeah, because you're 100% liquid, but you're
Gotcha.
liquid.
All right? So, because I don't have any refrigeration effect, my superheat's a lie, right? And my line is actually warm, it's not cold, and my TXV, and like I said, we'll talk about all that. So it's going to appear, to me too as a technician, I'm gonna screw my gauge on, I'm gonna put my temperature probe right here, right?
But
And it's gonna tell me I'm starving, and I'm gonna want to open that valve, okay? And it's already flooded.
Oh, yeah.
Right, it's flooding hard. It's flooding so hard I can't even tell it's flooding until I look at my compressors.
Try and explain it, I don't know.
And my black is turned white, right? What's going on? Okay, my green compressors are still green, but they got that nice little frost. And it's eating valves
It's Christmas time.
and washing out oil, and I got all those problems, okay? All right, so just be aware that it's very easy for these to overshoot. I see you pointing a finger, Chad.
You got a question?
Julie?
Why don't they just put like a port so we can measure the pressure? Because if it's not liquid, we should still be at liquid pressure, should we not?
So, no, we will have a pressure drop through the TXV.
It'll be a pressure drop, but it'll still be.
Yep, we have to calculate superheat to know it. And what we're gonna do, because we know that's gonna happen, we're gonna calculate superheat twice. We're gonna calculate it where the bulb is, right?
And the
And
intersection.
we're gonna go down a couple feet,
Yes, sir.
and we're gonna check it down there. Guess what? If that superheat is lower, that means I got a refrigeration effect between my two readings. I got liquid refrigerant.
It's on the rack now.
There's no way I don't, right? Does that make sense? That's how we're gonna check that. Now, when we go to set these valves, that also requires we set these valves a little differently, right? We're gonna start by turning off both of these solenoids. We're gonna starve the evaporator completely, right? Then we're gonna set up our superheat reading here, and we're not gonna hit the min-max buttons and walk away, right? We're gonna open one solenoid, just one, feed our case, and watch that superheat. And when that superheat hits 0, we know we flooded, we're gonna shut it off and start over, right? But we're gonna turn in our valve, and then do it again.
See
Okay?
that second part again? So you shut off both solenoids, then you're gonna set them one at a time?
We're gonna set them one at a time, right? And if they flood, recognize after they flood, it's gonna show starving. You're gonna think it flooded, you hit 0, and then you're gonna see superheat start climbing, It's like, oh, it's okay, it's at 10, it's at 12, it's at 20, it's at 30. Oh, it's starving, right? That's what it's gonna look like. It's gonna say 20, 30, it's gonna go 30, 20, 10, 0, 10, 20, 30, 40, 50, right? That's what it's gonna look like. If I don't see it hit 0, I don't know that it's flooded, right?
With the difference in sizes of those TXVs, you start with the smaller one first.
Sure,
Yeah.
best practice, yeah. Now, so just remember that, anytime that I'm checking superheat, I can do that too, right? If I'm not sure, right, I said we're gonna go farther down and take a reading. That may not be practical, depends on how the piping runs, right? Might pump out of the rack house right there and disappear, whatever. All right, I can always just turn them off. I can always shut them both off, as long as I've got some heat on that drop leg, then turn one on and check that superheat and watch it fall, right? That's the other way to check it. Either method will show me a flood. Yes, sir.
Would you want to set, like you're saying, you'd set your smaller one, then set your larger, would you want to then turn both of them on and set them, fine tune them
No.
that way?
Once I've set the superheat on each, they're gonna run that superheat.
Because your spring pressure's not gonna change.
Correct. That's right.
Constant superheat device.
Right?
You're gonna
That's
see
no
most
different than
turn that
having
on.
82 cases in the store and those TXVs not affecting each other.
So, I know you said turn one off and set them, but after we set both of them, would it be good practice to just turn both of them on, see how it runs there, make sure it's not flooding when it's both of them running?
So the only way that it wouldn't flood is if I had the appropriate heat,
Yep.
Yeah.
right?
You gotta have
So in other words,
line temperature.
yeah, if it's not hot enough to run them both and I turn them both on, they will flood, right? But the computer will prevent that from happening because of the staging, as long as my sensors,
That stage is only
are
gonna
good.
go on as it comes up in temperature.
as long as those sensors are good that we never check. I mean, we
check.
didn't used to check.
I check.
Or they put two different ones and they're all put different?
Right. Yeah, exactly. All right, so here's a little more modern setup. It's the same subcooler. Okay, and Kalos does these projects, right? We go in and take out the mechanicals and we drop in the electronic, all right? What's going on here? Super simple. We're just taking the two TXVs out. We're adding an electronic TXV. And of course, it has to detect superheat. So a pressure transducer and a temperature transducer. It's calculating superheat downstream and just opening and closing that valve. Okay, we've got a real challenge here. Here's a piece that's a miss in this strategy. Okay, this is a real problem that we run into. All right, where's the solenoid in this drawing? Right, they're not showing it, but it's in here,
It is.
right? We still have a solenoid, okay? What controls my solenoid? My EMS system.
Oh yeah, Walmart loves a pump with it.
Okay, so here's the scenario, all right? This liquid coming out, we hit our target. Let's say it's 50 degrees. This liquid comes out, it hits 49 degrees. My EMS system is gonna see that, right? It's gonna go to that surge. We're going to the surge, and we're shutting off the liquid to this valve. Okay, all good? Everything's fine. We got no problems, right? No problem. What's my Sporlan subcooler control doing?
It's trying to maintain your liquid temperature, and so the valve is gonna not know that that's liquid line solenoid.
All right, it's going to see the superheat climb
Yeah.
because I'm not flowing refrigerant. It's going to slowly, over time, because it's going to be looking at my liquid line temp and seeing that it's cold, so my PID is going to say, do this very slowly, right? What? Do what? Open, right? So my valve is going, my electronic valve is going to try to maintain that superheat. It's going to open. Very slowly, it's going to keep adding percentage, add a percentage, add a percentage. Okay? So how far?
All the way to 100.
Until we hit either a programmed stop or 100%. Valve's probably going to 100%, right? Now, my line sits there at 49 degrees all night. First thing in the morning, starts warming up, goes to 51. Solenoid opens. What percentage?
100%.
100%. Am I gonna flood?
Oh, yeah.
What's that gonna look like down here?
The pressure's gonna be higher.
Is this controller gonna see that it's flooding?
No.
No, it will, but it's gonna lag, no, it's gonna lag behind. which the damage is already done after
Yeah.
it lags behind. But then it's gonna hit your low superheat, that then shut off,
And
and
it's
it's gonna go
All
to
right,
zero.
so here's how this can play out. Remember, I just said, if we flood, it'll look like we're starving, right? But if we, as technicians, turn off that solenoid and set up our gauge and watch it, we'll see it hit zero and then climb again, right? Well, our controller's looking all the time. It's gonna see that happen. That's exactly how that's gonna play out. It's gonna see that superheat hit zero, and it's gonna say start closing,
25, 30
slowly,
Yeah.
right? Slowly, it's gonna say start closing slowly. So it's gonna go from 100 to 95,
Yep.
right? Well, meanwhile, now my superheat's climbing.
Yep.
Superheat's climbing because I'm flooded, and I've got liquid going down this pipe, right? And it's going, okay, it's working, let's go to 90. The superheat's still climbing, and it's like, oh, we went too far. Let's go back to 95, right? So we can walk in and find this system sitting here at 100% flooding that stew out of everything, and there'd be nothing wrong with it. The problem was it got cool last night, and I turned off the liquid line solenoid.
Christian's wondering why not just have that subcooler controller control the solenoid?
Yeah,
Well,
because
that's-
it doesn't have a digital out setting in it.
It doesn't need a solenoid anyway.
Yeah, it doesn't.
And it really doesn't, because the TXV is gonna close. It's gonna go to zero and it's gonna close.
Yeah.
Right, it might leak a little
Which is
bit,
why
it's
they
no
just
big
want a
deal.
remote monitor.
Yeah, no refrigeration, but, right, now, we're talking about this Sporlan version of that, right? That's what we're talking about. And you notice for you, I found an alarm.
Thank you.
You're welcome, because that's how we actually find
It
them,
makes
right?
me feel at home.
So we're talking about this version, right? But to Christian's point, it doesn't have to be this. Any EMS system that can drive an electronic valve
Yep.
can do this.
Yep.
We could have an S3C doing this. There's no reason why we can't. We can have a 521, we can have a 1081, we can have Emerson's valve drivers,
Yeah.
KE2's got a valve driver. Everybody's making a friggin' right? As long as it can read pressure and temperature and control the valve, it could be here. So anyway, so the subcooler control, we're not gonna go through that in depth today. Just know that there are many versions that can do this. Any valve controller can do this. This is just the one that's the most common for that particular customer, right? All right. What have I got going on here? I got the green compressors, and I got the black compressors on the same rack. So this, if I find this setup, right, this is my satellite setup. I've got a low temp or a medium temp rack, and I want to run a different suction group, but share discharge and liquid. Okay, same condenser, same subcooler, right? But after our liquid goes through the expansion devices, they come back to different suction headers. Okay, that's my satellite, nothing unique there. This particular version of that satellite is for subcooling. Okay, so when we look at these three compressors on the end here, that legend that I showed you that showed A and B rack subcoolers being separate, that's what, this is it, this is what it looks like. All right, there's a lot of different versions of this, none of them done particularly well. The real challenge with this is every one of them used the low pressure oil system. Right, that's been the real challenge. We went through that low pressure oil system, that OCV,
Yep.
right? Has got to be tied to my suction. Okay, but now I got two different suction groups, so I can't control my oil very well. And all of the challenges that we have with this are the attempts to have two OCVs or two different oil pressures, or some way to manage that,
Great one, they work great.
right?
Great one.
But you guys, you remember my high pressure oil class? It's about this. That's the fix. Just swap that whole system out with a high pressure oil system, problem goes away.
Yeah,
Right. But for whatever reason, that just hasn't happened. So we do find these constantly in the wild, and they're almost always off. They're almost always turned off. And the reason they're turned off is because someone doesn't understand how to balance all those pressures, because it's complex.
So that would be,
And it's not, and they're unique. They're almost custom built, every one.
I had to figure that out.
What's that?
would that be considered like outdated technology, since a brazed plate heat exchanger would be so much better?
So this feeds a brazed plate heat exchanger.
This is your
Oh,
second.
okay.
Yeah, and I don't have a drawing of it. But if you look at this drawing, we're not saying, this drawing says from medium temperature liquid header, from low temperature receiver, right, to medium temp suction header. Now, we don't have to do it that way, we can subcool ourselves, but this is that setup,
Yeah.
right? So that means that this refrigerant that's flowing through here comes from a different rack than this refrigerant that flows through here.
Same gas.
Yeah.
Right?
Yeah, same gas, just different compressors.
Okay, so they have to be the same gas type, and the only reason they have to be the same gas type is in case I have a leak,
Yeah.
right? This is a problem that plagues heat exchangers. All right, if I'm running water through one side and refrigerant through the other, and I have a leak, I'm gonna get water on the suction side, right? Yeah, CO2, glycol, both use plate heat exchangers, right? We can have a problem there. So when I'm designing this, there's no law that says I have to run 410 on both sides. I can run 410 on my primary side and chill 404. Sure, I can, right? It's just not a best practice because if I have a leak and they blend, right? Now, on this setup that I just showed you, they are running the same refrigerant because they've got common condenser, right? So the only way I'm gonna know I've got a leak, well, I mean, my subcooler's not working very well, but I notice A rack's refrigerant level keeps going down and B's keeps going up at an even perfect rate. All right, yeah, that's kind of how you know that, all right? The other way we may do this, we can do this a lot of different ways. The simplest is this suction header, and this liquid go to the same rack as this. Same suction, same liquid, right? If I do that, I get all the advantages of a mechanical subcooler except the energy savings. I don't get any energy savings because every BTU of work that this rack is doing, it's doing to itself. So, same suction group. It says minus 27 and my EPR is set at 47. Guess what? I'm doing that work at the same suction, minus 27. That's what my compressor has to achieve for that rack. I don't get any energy savings, okay? Because my compressor still has to run at minus 27. So just recognize that. If I'm subcooling myself, I'm not gaining horsepower, right? I'm getting the advantages of the smaller pipe. I'm getting the advantages of the steady temperature, hitting that TXV. I'm getting all those things, but I'm not saving any electricity. That one's got you thinking.
Wouldn't your rack stage list, or possibly even stage down, with the subcooler?
It won't stage down because it's the same amount of energy. It won't help it.
You're just transferring your BTUs from this half to this half.
Correct. Correct.
You're just moving the shell.
Correct. So that's the least efficient way to do it, right? Now, from there, the next most efficient way to do it, compound cooling. Right? You guys remember the compound cooling class? I think everybody's been through that here, right? I've got that interstage pressure. That's air conditioning pressures, right? Yeah, I can subcool off of that, and I do get that energy savings. I get that exact same energy savings, the big one, right? Modern version of that, low temp scrolls, vapor injection, right in the side, right? We covered that under compressors. Yeah, I'm gonna tie that subcooling right in there. That's interstage pressure, okay? That's medium temp. So I can do, so my rack, I can subcool my own rack and still get that energy savings if I'm using one of those two ideas, right? If I'm using just regular compressors, no, right? Next idea, low temp, and I'm gonna run these pipes to medium temp, just like this drawing says, right? We'll see that typically with pipes literally running between the rack houses, right? Typical store will have a 4-rack setup. It'll have A and B rack, low temp on one side, C and D, medium temp on the other. Yeah, we're gonna see that suction line, this suction line, and this liquid line running from C rack over to A, D rack over to B. Oh yeah. Not only did they do that for a bunch of years, we're gonna start doing that again as a retrofit. So Kalos is probably gonna get some of that action this year, this coming year, or the year after, right? We're gonna start adding that piping, right? Because especially as we put in these HE cases and you see the load on the rack getting smaller and smaller, and they're telling us to valve off compressors because the rack's too big. Wow, you got room for a subcooler? Why would you do that?
Yeah.
Right? Well, somebody figured that out, so we will be doing that. Okay? Right? Okay. Any questions about subcooling?
Why is it so cool?
I will say that it is absolutely imperative that you always check with your gauges, your superheat on those.
Verify.
Because there's, yeah, well, because majority of them have flip-flop sensors, but moreover, they're also uncalibrated, and that's the real big downside of that is there is one bad side about all the electronic valves and everything is that they are slave to a pressure transducer and a temperature sensor, and if either one of those is off, it can be catastrophic to everything downstream.
That is the most common problem. On our drawing, we've come through, our liquid we've gone through the primary side of our subcooler. Now our liquid coming out of our receiver has gone through our dryer, it's gone through our subcooler, and it's coming back up, and it's gonna hit a valve here. Not always, right? There's some stores that use this, some that don't. There's a few different versions of this idea. We're not gonna spend a ton of time talking about hot gas defrost. I'll probably do a class on that on its own when we get a customer that uses hot gas defrost. Most of our customers are not using hot gas defrost, so I'm not gonna spend a ton of time talking about it. But I am gonna talk about alternatives that our customer does use that are very confusing and cause us some real grief, okay? So this version, what they've got drawn in here is an OLDR valve, okay? That is for hot gas defrost. That particular valve is for hot gas defrost. I just said I was gonna talk about that, right? But hold on, right? There's a function of this valve, and this valve, my liquid coming out of here and going towards my liquid header that's gonna feed my cases, right? This valve is gonna reduce the pressure of the liquid that comes out and goes to my cases, right? Now the reason it's gonna do that for hot gas is so that I can bring hot gas through my evaporator and it'll flow from high pressure to low pressure. I want to tie into that header. That's why I'm gonna do that, right? Once again, I won't go through hot gas defrost too much. I lit up a light bulb on your head just now, didn't I?
Yeah, thank you.
We'll cover that, like I said, in another class, maybe at the end, but, all right. So that's restricting liquid flow to my cases, right? Now, our other customer who doesn't use hot gas defrost, does understand hot gas defrost, looked at this idea and took it to an extreme, all right? Now, the advantage of controlling my liquid pressure going to my TXVs, there's an advantage to that. Remember, when we were talking about the efficiency of the temperature, I threw out there that I also have an efficiency change by pressure differential. Well, if I can maintain the same pressure to my TXV and the same liquid temperature year round, my TXV setting will be the same year round. Okay? That emphasis really should come at the end of my sentence, not in the middle. You know, it kind of didn't punctuate that very well. All right, so anyway. So you guys have just walked in. We're skipping the OLDR. I gave a very quick overview of it, but we're going to talk about LPR, liquid pressure regulator, all right, or open pressure, the outlet pressure regulator, OPR, outlet pressure regulator. It can be called both things. It can be labeled both things. In most of our stores, this is actually a retrofit, and it's not labeled or called either one. We just find a strange setup here we don't quite understand, right? And there's no tags, there's no labels, it's not on the drawings that added, right? But if we find it originally from the equipment manufacturer, if it was installed on the rack, it's going to be labeled one of these two things, LPR or OPR, all right? So let's go through what this is all about. Okay. Here's a drawing very similar to what we've just got finished talking about, subcooling, right? All right? So what I'm going to do is, on my primary side, no change, right? I've got my TXV that's going through, I got my EPR, right? My secondary side is where I'm going to have something else going on. I've got my receiver, I'm going through my filter, now I hit my subcooler, all this is the same, no difference. I'm coming out of my subcooler. Now this is my liquid that's going to my case. This is my secondary side. This is my now subcooled liquid, right? I'm going to run it through a pressure regulator. Oh, this is different,
I like it.
all right? This is different.
It's a little,
So-
hold that?
So it's kind of like a holdback, right? Except now I'm holding back at my subcooler. I'm not flooding my condenser.
I've seen those.
What am I gonna flood? If I hold back here, where's that liquid going?
Separation.
Subcooler.
Where?
Subcooler.
It's gonna go through the subcooler, which is always full of liquid, right? So then where?
Back to the
Receiver. Oh, okay. So this is a restriction of the liquid line that's gonna flood my receiver, right? Yeah, that's what it's gonna do. So when this guy's in play, I may see my receiver sitting at a very high level. Not extraordinarily high, 40, 50, 60% maybe. Okay, that can happen.
You're above your switch.
What's up?
You're above your little alarm switch.
Right, I'm not alarming, right? So when I'm charging a rack, I need to be aware if this is got this feature or not, right? If this feature's engaged and I bring it up and I clear my alarm at 20% and I throw in another drum or two, right? Oh yeah, I'm gonna alarm when this guy comes into play, right? We see what's going on there, right? And we'll talk about what controls this and how it's controlled in just a minute. But what we want to understand is that this is an outlet pressure regulator, OPR, right? Which means it's controlling the outlet, not the inlet. Okay? It's controlling the outlet side. It's controlling my case side. That's different than all of our other valves that we've been talking about, except the A9. You guys remember the A9 was controlling the outlet, right? Wait a minute. That's a damn A8. All right, we thought we had the A8 nailed down, didn't we?
Never.
Huh? Yeah, there's one more variant to the A8. All right, we're using an A8 here in our model number. It's an A8 with an O for outlet. All right, so anytime I see an A8 valve that has an O in that string of letters, it's not an EPR.
Outlet.
It's controlling the outlet, not the inlet. It's not a sporet with the I for inlet, right? It's an O for outlet, right? Same exact valve, it's just controlling the other side. Now, it's controlling the outlet, and it's going to control that to a pressure, not to a differential. Right? In other words, I can set it to 150 and it's going to stay at 150. My discharge can go up to 250 or all the way down to 150 and it's going to stay at 150.
Yep.
Right? It's not giving me 20 pounds difference. Right? You understand the difference? Okay? All right. So it's going to be an A8. I'm going to find an A8, and this is also can be a little confusing if I'm trying to figure out the piping on my subcooler, because often the EPR on my subcooler is an A8. Well, now I've got an A8 on the top pipe, and then my liquid coming out on the bottom. Got an A8. This will confuse the daylights out of you if you're not prepared for it, all right? One of those A8s is going to have an O in it. That's my liquid line going to my case, all right? Okay, the other one's going to be a sport valve or port valve, right, with an I. It's going to be my EPR. So there's one more feature of this we really need to understand. When we pull up the O version of our A8, it's going to show an external connection to a pressure tap. All right. Now we're measuring the pressure right after it, so it's unnecessary, and that's going to be plugged. Okay. But all the documentation that we find on this valve is going to show a pipe coming out of there. Right. So don't be confused. It is that valve. We just don't need that because we're measuring the pressure right there. Okay.
So, you know the, do they have what's it called? The old Sorts, the Sort 12s.
Right? Sure.
They have those kits where you can just take that, it's got like a little lock ring, and you can thread in a EPR to that. So do those have something similar to where you could just take those 4 bolts out the thing?
Absolutely. So what he's talking about, guys, is taking an A8 valve, a mechanical A8 valve right here, leaving your torch on the truck, unbolting this valve, and screwing on a CDS valve, an electronic stepper motor.
There's a,
Yes, they absolutely make that kit.
Give it a
there's a
heart
video on
transplant.
YouTube that you can get.
Do what?
Give it a heart transplant.
Yeah, exactly.
Yeah.
Right, so yeah, you can do that.
9 or 12.
Does it work? Yeah, really well, right?
4-minute
I
video
was
on
wondering if we
YouTube
should
on
try
how to
to, CO some of these.
unbolt, take out,
Why not?
put in.
Because they usually control well enough, right?
Your wire.
There are a few instances where that really makes a lot of sense, usually on the drop leg, honestly. But if I've got a massively oversized system now, originally it wasn't oversized, but we've just changed a bunch of cases and we put HEs in, and we got an A8 valve we're trying to control it with, and our mass flow is way low now,
Some energy?
and they didn't have us change the copper, and we're trying to dial in that EPR, and the thing just keeps slowly moving around because I don't have enough pressure drop across it, because I'm not flowing enough flow, because it's massively oversized, right? The right thing to do would be to put a smaller orifice, A8, change cartridge. But I could also just drop an electronic on if I'm gonna spend that kind of money. Yeah,
Tell me where the cartridge is.
what's up?
Where's the cartridge?
That is this big blue piece right here in the middle.
Oh, okay. Well, that's what I thought.
That's
If
one
there-
giant
if there were
cartridge.
another curveball,
It's it's like a 10-pound cartridge, right?
Yeah. Okay.
Big old chunk of steel. It's got the piston in it and all those things, right, including the orifice. Here's another feature that I'm gonna have in this system. That is a bypass. I'm gonna be able to bring that refrigerant up, run it through a solenoid, and go around my A8 valve. I gotta have that ability also, okay? So anytime I find an A8 valve in the liquid line, going to my cases, I'm also going to find a bypass with a solenoid. Now, here's why most of us don't really understand how any of this works. That solenoid looks like a regular solenoid. It is not. That solenoid is
No.
normally open. Normally open. So when I see that energized, when I see it lit, as a technician, I'm thinking it's open, but it's really closed. And that's why when I try to reason through what the heck it's doing, it doesn't make any sense, because it's backwards. It's because the valve itself is actually normally open, not normally closed. And it looks just like all of our normally closed valves. They're on every single liquid line, right on down the line. There's 17 of them all in a row, and I got one more, and they look the same. It's exactly reverse acting. It's normally open.
Typically, they'll have that little washer thing on top of them, right?
It'll be the same, there's no difference. The model number is the only thing that'll give it away. The arrow, it'll have the arrow. It takes an MKC 1 or 2, depending on its size, just like my other solenoids. Yeah, the little washer thing will be identical, okay? Snaps on the same, there's no difference, right? Okay, so that's just one of those things I gotta know.
Old faithful.
No, this is what you want.
We're all showing off our
Our magnet testers.
magnet testers.
Good old
Okay.
live is always there.
All right,
Step it up.
so it's gonna light up and it's gonna energize the same as any solenoid. It's just gonna make the opposite thing happen that our brain is telling us should happen. So here's the concept. If I reduce my pressure differential across my TXV, if I reduce it, in other words, I make my discharge pressure, I'm not gonna change my suction is gonna be stable, right? If my discharge pressure comes down, right, then the pressure differential from the discharge to my suction through my valve, through my TXV, is gonna go down. When that happens, my expansion valve becomes less efficient. It shrinks, it gets smaller. So if I got a 1.5 ton valve and I change that pressure, it's gonna be less than 1.5 ton capacity. Right? If I increase that pressure, the opposite happens. The valve becomes more efficient. My 1.5 ton valve is gonna be worth more than 1.5 tons if I cross that point. Okay? Well, this valve, this outlet pressure regulator, is lowering that pressure. It's making my valve smaller because the pressure differential is less than it would be without it. Does this make sense?
Yep.
Everybody with me? Doesn't sound like a good idea at all, right? Sounds kind of backwards. Isn't that the opposite of what we're trying to do with the subcooler?
Yeah, but if your load reduces,
All right, so I may hit that low pressure anyway, is your point, right? Yeah, I will. And when it's cold outside, and I've got light load, Can my discharge pressure fall? Yes, it will fall, of course, right? All right, my subcooler does the exact opposite. For every degree that I take out, my valve gets bigger and bigger, right? More efficient. All right, the reason why this outlet pressure regulator is right here at my subcooler is because they're gonna work together. If I'm sending out 50-degree liquid at 138 PSI, my 1.5 ton valve is gonna have the same offset factors. They're about 1.5, and we will cover that. About 1.5 times, right? They're gonna cancel each other out. My 1.5 ton valve is gonna be pretty close to 1.5 tons. All right? Now, here's where things can go wrong. My subcooler goes down. Now I've lost efficiency out of this side, and I'm not getting it back on the subcooling side. I've just lost efficiency. Now my valve's not big enough. Really. Right? Case is gonna run long. I'm gonna have high superheat. So if that happens, if my subcooler is not subcooling, I gotta open this bypass
Yeah,
so I don't restrict that pressure, and I get my differential back up high so my valve acts right, acts the correct size. Does that make sense? So that means I'm gonna tie this solenoid into the solenoid feeding this EEV. They're gonna be tied together. Okay? Anytime my EMS system shuts off my subcooler, it's gonna open that bypass. Now, you just heard what I said, EMS system. Not my little subcool control from Sporling. All right, we can still have that same phenomena happen where my temperature on this leading line gets lower than the set point on this, and we turn off this solenoid, we open this solenoid, and this guy goes to 100%. It's still gonna happen. Yes, sir.
you make a good point, but now it also raises a question, so is this a dead technology now that we have the CDS valves from Sporling? Because that's not hooked up in it, for the liquid pressure, I mean, that's all internal to Sporling, so they're not gonna be able to reference anything on the rack side to react.
All right, so yes and no, right? The way that we're typically seeing it used is no, it can't. And the reason it can't is because also, not to get brand specific, but most of these are Spectrum Novar systems, right? They're old Novar stuff that can't communicate through BACnet, right? That Sporling controller can talk BACnet. So the other thing that we're seeing happen is when we're upgrading that old Spectrum stuff to Opus, Opus can talk BACnet. We can cable the Sporling controller to the EMS system and address it and make it a component, and it will now talk, right? Emerson's been able to do this all along, okay? And so is Danfoss.
Yeah, and you never had, I just know some of the stores that I've been to.
Yep. So the majority of our stores, when this conversion happened, were running Novar Spectrum.
Yeah.
There was no point in time when together they couldn't talk, right? Now we're actively changing all those Spectrum systems to something else, either E2s or mostly Novar ES1s or ES3s, right? So that means they can. They'll have the ability as we do that. That should be one of the features that we're doing is tying in that comm loop. Doesn't always happen. It's not up to us, right? They pay us. They draw blue lines and pay us to go do the blue lines, and it's not included. It's just not included. But it can be and should be. On the newer stores that you're seeing built today, they're all wired that way, right? I say the last 5 years, 4 years, something like that. You'll find they're all networked, right? And they are passing data, and that doesn't happen. That solves that problem, right? That is a real problem. All right. So anyway, the big takeaway here on this regulator is when my subcooler turns off, I'm going to bypass. That's why that's happening. Okay? That's why that's happening. Which means when I'm standing there watching this thing click on and off, and I don't know why, right? It's probably just simply the EPR.
Too cold.
It's too low, and I'm cycling. I'm cycling my subcooler, and I don't see that, but I see my liquid pressure going like this. I sure see that, right? Because it's all over the freaking place. Yeah.
God, we see that so much.
All right, so they're just tied together. That's the big takeaway. Now, what pressure do I set this at? It's an A8. That means it's I'm mechanically dialing in a pressure here.
15 PSI less than your
All right.
something else.
For hot gas defrost, he's absolutely right. For hot gas defrost, 15 pounds is what I want, right? But that valve is giving me a difference. It's not a fixed setting, right? It's gonna be 15 pounds, and then when my discharge goes up, my liquid pressure goes up, it goes up with it.
Yeah.
It's always 15 pounds. That's the big difference between this system and that system. Yes, sir.
Would it be whatever the engineering of the TXV is?
All right.
Compound answer.
Absolutely, okay? And we're actually gonna get into that. We're actually gonna cover the engineering on how that works on a TXV, right? When we get into TXVs, it's really a good spot to do that. But know this, the correction factor, we're gonna use a correction factor when we're sizing our TXVs. The correction factor for pressure drop is 1 for 100 PSI. What that means is I'm gonna multiply my tonnage by nothing, by 1, at 100 PSI. Okay, well, let's back up on that.
Yeah.
All right, that means if my suction is 50 and my discharge pressure is 150 and my valve says it's worth 1.5 tons, it's worth 1.5 tons. That 100 PSI is what it's designed to run at, okay? 100 pounds. Now, if I go less than that, I've got to start making that valve smaller in my calculations, okay? It loses efficiency, okay? So 100 pounds, I don't have to have 100 pounds, right? But things start getting wonky once I get under 100 pounds, all right? So when we design things, we really don't want to go below that threshold. You'll hear me say 90 a lot, right? 90 pounds, our valve tends to work okay, right? We're right on the edge of that, but it's okay, it'll work.
This is a PSI value that you're.
All right, the difference between my suction and my discharge.
Oh, okay, difference, okay.
Different, okay, differential through the valve,
Okay.
all right? Once we start getting lower than 90, our valve not only starts shrinking, but it just doesn't control very well, honestly. The closer we get to 0, the less it's gonna work, all right? So when we have those low ambient problems and we got cases running warm in the store because we don't have enough discharge pressure, where's that happening? That's happening about 90 pounds, under 90 PSI, all right? Well, that means this outlet pressure regulator, we're always gonna set it at least 90 pounds, our highest suction,
Yeah,
right?
okay.
All right, now, when I say our highest suction, we haven't got into EPRs yet, but I'm talking about the highest EPR on the rack, because that's the differential, is the TXV for that case needs to be at least 90.
And that's the same backwards engineering that you used for the head pressure control.
Yep.
Okay. So you could set that outlet pressure regulator for the same, roughly the same pressure as your holdback valve.
So they're not gonna be terribly different.
Far off, right?
Yep,
10, 15
yep,
PSI. with
exactly,
each other.
exactly.
Okay.
Yep, okay. All right, so, you know, just a practical example, let's say that artificial rack I just made up with 50 PSI suction, right? If my warmest evaporator was 50 degrees, 50 PSI was its setting, I would set this outlet pressure there to 150 pounds,
Gotcha.
Yeah.
right? And since I can go to 90, I could go to 140.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.